All right, we're going to go ahead and look at the next section today. We're going to talk about another way we can integrate some functions, aka work backwards. And up to this point, we should only really be familiar with these 5 integrals or antiderivatives. And then today we're going to get into some that are a little bit more involved, not difficult, just involved, because we're going to spend our time talking about them. But if I asked you to work backwards from any of those 5, would you be able to do it? Some are a little bit easier than others.
Oh, we were doing dissections.
That's okay. How'd it go?
Good.
Disgusting?
No.
No? It was fun? Can we think about if we work backwards from cosine, what did we have before? If we work backwards from sine, what did we have before? Maybe you want to work backwards from x to a power. Think about it this way. What do you have to take the derivative of that would give you sine? What can you take the derivative of that would give you cosine? Another way to think about it. Let's start with the first one. How do you want to work backwards from x to a power? What was that kind of reverse power rule process? Alright, so we would have x to the 5th, and then we got to divide the coefficient by 5. So 1/4 divided by 5 would end up being a 1/20. You can take the derivative of this to check it, and you better get that as your answer. Don't forget the plus c. Okay? What about the next one? What can you take the derivative of that would give you cosine? The derivative of blank is cosine. Do you know how to take derivatives? It'd be positive sign. The derivative of sine is cosine. Close. This one's negative. And working backwards from sine would be negative cosine. Okay. I hope we're okay with these. What about the last two? These are a little different. What can you take the derivative of that would give you 1/x? Or what can you take the derivative of that would give you e to the x?
1/x is natural log of x.
Natural log of x. Good. Remember, the derivative of natural log is the derivative of the inside over the inside. So that would be 1/x. What about e to the x? It's just e to the x. Good. If you took the derivatives of any of these, you would get those. Okay, we're going to work backwards. We should be familiar with these 5 up to this point. We're going to talk about another way we can work backwards. And working backwards from this section, remember how we had the chain rule for derivatives? Okay, kind of if we have an inside and an outside piece, we're going to have to identify those when we're working backwards. So what we're going to try to do here, just to make a connection or relationship, we're going to practice our chain rule with some of these examples, and then we're going to see how we can work backwards from a chain rule. Okay, integrate a chain rule. So take a look at the first one. If we wanted to figure out the derivative of f of x, maybe you want to put the 3x in parentheses, if that helps you out. We would need the derivative of the outside. So the derivative of sine is cosine. We'll keep the inside, which was 3x. Then to finish off the chain, we multiply by the derivative of the inside, which would be 3. So maybe if we want to clean it up, move that 3 out front, we'll have 3 cosine of 3x. Okay, we're going to fill out the derivative column first, just because that's what we're familiar with using that chain rule, and then we'll talk about how we can work backwards. Okay, what about the derivative of e to a power? How does that work? Okay, so the e to the power stays the same, and then times the derivative of the power, we would have a negative sine x. Good. If you want to rearrange it, maybe we'll write negative sine of x out front, and then e to the cosine x. Doesn't really matter. Order doesn't matter when you multiply. All right. Well, how do we find the derivative of a natural log?
Derivative of the inside over the inside.
Over the inside, yep. That's it. We can't really clean that up at all. All right. And the last one, maybe you want to rewrite this as a power of a half instead of that root. So our chain rule, let's bring down the 1/2 power. We'll keep the inside. Our new power would be -1/2. And finish off the chain, we got to multiply by the derivative of the inside, which would be 2x. Let's clean it up though. We have a negative power, so something's going to move to the bottom. And then we have a 1/2 times a 2x, so the 1/2 and the 2 would cancel. Looks like we'll have an x up top, and then the square root of x squared plus 3 on the bottom, because it had that negative power. Alright, so hopefully that's a good review of our chain rule. Inside, outside derivatives, maybe derivatives of e exponentials, derivatives of natural logs. We got to be familiar with those. So what we're going to try to do today is work backwards. What if I wanted you to integrate 3 cosine of 3x? Okay, what if I wanted you to integrate this derivative? We know, hopefully, that we should get back sine of 3x, right? If you integrate a derivative, you get back to where you started, okay? But there's a particular process that we're going to talk about today called U substitution. Sorry, you can't see it. U substitution. The reason it's called U substitution is because we're going to change this complicated integral into something more easily done for us. We're going to change that into one of the 5 that we're familiar with on the board. And in order to do that, we're going to change some things or substitute in some values. So we're going to change a complicated integral into an easier one for us. Okay? Now the first thing that we're going to do is we're going to identify the variable u. This is why it's called u substitution, because they just use the variable u. We're going to let u represent the inside of the function that you're integrating. So when you take a look at this 3 cosine of 3x, what do you think is representing the inside? Just like 3x, just like how a chain rule is inside-outside parts, our U substitution has to utilize those inside-outside parts as well. So the inside maybe we'll label as 3x. What we're going to do is take the derivative of this inside that we just identified. Now, whenever you take the derivative of u, that would be du over dx. Instead of dy over dx, like when we take the derivative of a y, we're taking the derivative of a u, so it's du over dx. What's the derivative of 3x? 3. Good. All right. You might have to write a little small in these boxes. Okay, I should have made them a little bit bigger. Hindsight's always 20/20. What we're going to do is use these 2 u equations, okay, the u and the derivative of u, to help us rewrite this complicated integral. Okay, so let's first start with this. We're going to keep the 3 in the cosine because we didn't really identify that to be anything. But instead of 3x, what can we substitute into its place? This is why it's called U substitution. U, right? Instead of 3x, we said that would be U. Now what we're going to do is rewrite the dx on the end. Because what we're trying to do here is change an integral with x's, a complicated integral with x's, into an easier integral with u's. This is where the derivative equation is going to come in. So if you were to solve this for dx, you would basically have to switch the dx and the 3. You would multiply the dx over, and then you would divide the 3. Can we visualize that without me having to write it down? Can you see how those would switch? So instead of dx, we'll have du over 3. Notice how all the x's are gone, right? We just have u's in there. Do you notice anything that's going to happen now that we rewrote it? The 3's will cancel. So all we're left with is the integral of cosine of u du. Can we work backwards from cosine? We did it on the board. It'd be sine of u, let's not forget the plus c. But what did we say u was again? U was 3x. So what if we substitute that back in? We get sine of 3x plus c. Does that match the f of x that we started with? Sine of 3x, right? Okay. So u substitution, it's kind of a process, and we're going to do a bunch of these so it starts to sink in, but it's a way for us to work backwards from a complicated integral. If we can identify an inside piece, we're going to let that be u. That way, when we find the derivative of it, maybe it'll cancel something out or simplify to something a little bit better for us to use. All right, let's try the next one. So we're going to work backwards from negative sine x e to the cosine x. We already know what our answer should be. It should be e to the cosine x, that original function we started with. But let's see if we can get there using u substitution. So the question is, in this case, what do you want to let u be? What is considered kind of the inside of an exponential? We have that base of e in there. Let's try the power, okay? So we'll let u be cosine of x. We're now going to take the derivative of that. So du over dx, the derivative of cosine is negative sine of x. So now that we have our u equations, we're going to rewrite the complicated integral with x's in it into an easier integral with u's in it. All right, now I did not do anything with this negative sine of x. The only thing I did was let the cosine of x be u. That was it. So everything else is going to stay the same. Negative sine of x times e. Now instead of being to the power of cosine, that's to the power of u. Now we have to rewrite the dx on the end, and that's where the derivative equation is going to come in. The dx and the negative sign are just going to switch if you were to go through and solve. So we'll have du over negative sine of x. Do you notice anything that's going to happen? Negative sine x is canceled. Okay, the x's should always go away. You should only be left with u's. That's why it's called u substitution. So what if we work backwards from just e to the u? It's just e to the u, like we did over there on the board. So we've e to the u plus c. But what was u? What did we label that as? Wasn't it cosine of x? So we have e to the cosine x plus some constant. Doesn't that match what we started with? right? So we know this u substitution process is working for us. Eventually we're going to get to the point where we don't know what we started with. That's going to be the real test. Are we doing okay? Kind of, it's new to us, okay, but we're going to go ahead and kind of get into a groove the more of these that we do. Let's try the next one. Okay, we're going to work backwards from 2x over x squared plus 3. What do you want to let u be? What do you think is considered the inside of a fraction? Let's try the denominator. What if you were to take the derivative of the denominator? You get 2x. Isn't that the top? Okay, so do you see how strategically picking the denominator, the derivative is showing up somewhere else in that integral? Maybe that might help us. For instance, take a look at the first one. If we let u be 3x, the derivative of 3x is 3, and notice how that's showing up somewhere else in the integral. So maybe you can find that kind of pattern there. Whatever you let u be, the derivative of it should probably be showing up somewhere else. That might be a guide to help you. So we'll let u be x squared plus 3. The derivative of that, du over dx, would be 2x. So with those two equations, we're going to try to rewrite this original integral. All right, so the only thing I did was I let the denominator be u. That's the only thing I changed. So the 2x is going to stay the same. If we were to rewrite dx, or solve for dx, it would switch with the 2x derivative that we found. So we would have du over 2x. Anything going to happen? 2x's cancel, so it looks like we're just left with 1 over u du. If we work backwards from 1 over u, what's the antiderivative? Natural log, right? 1 over x, the antiderivative was natural log of x. So this would be natural log of u. Don't forget the plus c. And we identified u to be x squared plus 3. Doesn't that match the original function? Natural log of x squared plus 3. Do I need to make those boxes bigger? Yeah. Sorry. I'm trying to write as small as I can, but these markers have kind of a fat tip on them. I'm hoping we can write a little smaller. I'll have to make them bigger next time. Make a note of that. All right, let's try the last one. We're going to integrate x over the square root of x squared plus 3. What looks to be the inside?
Square root.
Okay, inside the square root, we'll do x squared plus 3. What's the derivative of x squared plus 3? 2x. Okay. Now, notice how in the integral, we don't exactly have a 2x, but we do have an x, right? So the derivative isn't matching exactly, but it's kind of there. Okay, we'll see how this is going to operate. So let's go ahead and rewrite the integral. We're going to keep the x up top. And in the bottom, we have the square root of u. Instead of the dx on the end, we're going to solve for it. If we just switch the dx and the derivative, we'd be left with a du over a 2x. What's going to happen? the x's cancel. The x's should always cancel. Okay, we want to make sure that we're just left with u's. We're only working with one variable at a time, so the x's should go away. We should just have u's. So let's take a look at what we're left with. We essentially have a 1 over 2 because we have a 2 left in the denominator. And maybe instead of having the square root of u in the denominator, what if we brought that up and wrote it as a negative 1/2 power? That might help us a little bit. Can we work backwards from 1/2 u to the negative 1/2 power? Think about the top example that I did over there on the board. We got to work backwards from a variable to a power. What do we do? Add 1 to the power, so that would be to the power of 1/2. And divide by this. So we're going to take 1/2. 1/2 divided by 1/2, which is 1. Anything divided by itself is 1. Let's not forget the plus c. What was u again? We said it was x squared plus 3, right? So we have x squared plus 3 to the 1/2 power plus c. Isn't that exactly what we started with? Sounds good. All right. So this u substitution is a way for us to work backwards from the chain rule. But it all hinges upon identifying what is that inside stuff. So just as kind of a mathematical representation here, if we were to take the derivative of kind of a function inside of another one, this is when we would use the chain rule. We would need the derivative of the outside, which we can represent as f prime. Make sure we keep the inside function. And then we would multiply by the derivative of the inside, which would be g prime. But if we want to work backwards from that chain rule, we're going to utilize u substitution. This whole like u equals the du over dx equals, and in the end we know we should get that original function back, that f of g of x. Don't forget the plus c if you don't know the bounds. Alright, so what we're going to do for the rest of today and tomorrow is we're just going to practice this u substitution. Let it kind of sink in. Hopefully it becomes kind of muscle memory to a point because we're going to do so many of them. But we're just going to practice, practice, practice. I'm hoping these boxes are bigger. A little bit. Okay. Let's take a look at the first one. Maybe we want to put the 3x in parentheses because sometimes trig functions have them, or at least they should, in my opinion. What can we label as u? 3x. That's kind of the inside of that function that we're starting with. The derivative of that is 3. So we're going to go ahead and rewrite the original equation, making sure that we do the appropriate substitutions, and eventually all the x's go away. So we're going to keep the 3 in the cosine. Instead of the 3x, we're going to substitute in u. And solving for dx, we would get du over 3. Did all the x's go away? We don't have any left in there, right? We just have u's. Anything else going to go away? The 3's. One's being multiplied, one's being divided. So instead of solving or integrating the complicated derivative that we started with, the one that had x's in it, let's go ahead and try to work backwards from this u integral. It's a little bit simpler. If you work backwards from cosine, what do you get? What can you take the derivative of that would give you cosine? Just sine. Close, that's okay. So we would write sine of u plus c. But our last step, we could probably substitute back in that u value, which we said was 3x. There's our antiderivative. If you wanted to check your work, you would have to use the chain rule on this answer, and hopefully you get 3 cosine of 3x. Okay, you can always check your work. That's what's nice about these. Let's try the one below it. Okay, another trig one. Is there something we can identify as the inside part? Oh, we're doing, sorry, you went to the one over here. We'll come back to that one. There we go. 2x plus 3. If we take the derivative of that, we would just have 2. Let's go ahead and rewrite the original integral. So we're going to keep the 2 in the sign. Instead of 2x plus 3, we said that will be u. And instead of dx, we'll have du over 2. All the x's are gone, which is fantastic. And is there anything else we can simplify? Notice how the 2's go away? So can we work backwards from sine? Let's see, this would be negative cosine of u plus c. And if we go ahead and replace the u again, we said that was 2x plus 3. We doing okay? Maybe we're on a roll, maybe we're not just yet. We'll see. Let's go ahead and jump back up to this corner one. Is there anything that you notice to be on the inside? We'll let that be u.
Inside the, oh, wait,
That is a cube root, yes.
that's right.
So we'll say x squared plus 5. I know the 3 looks like it would be a power on the x. I probably should have separated them a little bit more, but that is a cube root. If we take the derivative, we would get 2x. That was interesting. All right, let's go ahead and rewrite the integral. So I did not do anything with the 2x, and I need the cube root of u, so maybe I'll write that as u to the 1/3. And instead of dx, I'll have du over 2x. Did the x's go away? Yes. Even not initially, do you notice how they'll cancel each other out? There we go. So instead of trying to work backwards from that complicated x integral we started with, we're going to work backwards from u to the 1/3, which is so much simpler. Let's go ahead and add 1 to the power. So it'd be u to the 4/3. And then we need to divide the coefficient of 1 by that power of 4/3. So our new coefficient would be 3/4. It would do a little flip. Don't forget the plus c. All right. So our final antiderivative, we would have 3/4. We identified u to be x squared plus 5. We would have a power of 4/3, and don't forget the plus c. Are we starting to see the process a little bit? They're all the same. The tricky part is trying to figure out what u should be. If it doesn't work out, maybe try something else for u. Let's try the next one. What do we want to let u be? Keep in mind the derivative of u should kind of show up elsewhere in that integral. Let's try the denominator. The derivative of the denominator is 2x plus 2. And that's the numerator, so it kind of seems like we chose the correct u value. Let's go ahead and rewrite the integral. So we let the denominator be u. That means the numerator is going to stay the same. So 2x plus 2 over u. And when it comes time to rewrite the dx, we'll do a little switcheroo. We'll have du over 2x plus 2. Do the x's go away? Notice how 2x plus 2 up top, going to cancel out with 2x plus 2 on the bottom. So we got to work backwards from 1 over u. What is the antiderivative of 1 over u? Maybe think about 1 over x over there on the side. Do we see how it would be a natural log? Natural log of u plus c, and then we can substitute in the u value. So natural log of x squared plus 2x plus c. Okay, so with all of these, you can check your answer by taking the derivative, and you would specifically have to use the chain rule to help you do that, because we are working backwards from the chain rule. If you wanted to, you can check it out. Derivative of inside, 2x plus 2, over inside, x squared plus 2x. Looks like it checks out. Do you guys think you can try one on your own? Try the cosine one.
We're working on a thing for next Tuesday.
Yeah?
It's taking forever.
Thank you. We're going to do it tomorrow too. And maybe the next day. We're going to take our time. All right, let's just see how far we can get. I understand if we can't get it all the way to the end. If you can, more power to you, but baby steps. What did we let u be? 3x plus 2. I agree. Could we choose that? Okay, what about the derivative of that u equation? 3. Are we good so far? All right, we're going to rewrite the original integral. So we have the cosine, but instead of 3x plus 2, we're going to label that as u. And instead of the dx, if we were to solve for dx over here, the dx and the 3 would do a little switcheroo. So this would be du over 3. Could we get that? Did all the x's go away? So far, so good. Okay. Now, what's a little tricky is you may have to rewrite this so that it's a little bit easier for us to work backwards. Instead of having the division of 3 over here, what if we move that as a 1/3 out front? It's the same exact thing. We're just in a different spot. Can we work backwards from 1/3 cosine of u? It would be 1/3 what? Just sine. Just sine of u plus c. Last but not least, we know what u is. We said that was 3x plus 2. There's our antiderivative. If you wanted to check it, you'd have to use the chain rule, and you should get cosine of 3x plus 2 back. How do we do? Could we get to a point at least? Okay? Choosing u and du are kind of the trickier parts. Okay? Rewriting, we'll get there. Okay, but for now we got to make sure that we choose the correct u. What about the next one? What do you want to let u be? I agree, that's an inside, okay? And if we take the derivative of it, we'll get 2x. So the other part of this integral is the 3x out front. That's kind of similar to the derivative we have. Not exactly, but it's still very similar. Let's see how this is going to play out. So if we rewrite the integral, we're going to keep the 3x, we're going to keep the square root, but instead of the inside, we're going to label it as u. Now also maybe instead of the square root, we'll put a power of 1/2. Instead of the dx on the end, we'll do a little switcheroo with that derivative of 2x, and we'll get du over 2x. Will the x's go away? Yes. But notice how we're left with a 3 divided by a 2. So very similarly to how this cosine 1 example worked, maybe we'll move that 3 over 2 out front as a coefficient. So instead of having to work backwards from that complicated square root x integral, we now just have to work backwards from this simpler u integral. Can we do that? If you add 1 to the power, we'll get 3 over 2, and then divide the coefficient by that new power. 3 over 2 divided by 3 over 2 is just 1. Don't forget the plus c. So in the end, if we were to replace the u with what we originally labeled it as, we'd have x squared plus 2 all to the 3/2 power, and then a plus c. All right, this was just meant as an intro day, so we know what to identify, what to look for, kind of how it works, but we're going to spend a bunch more time tomorrow, and maybe even the next day if we have to, trying to get used to this u substitution. Okay, practice, practice, practice. You got to try them and practice them so you gain more confidence with them.